So let's go through that. Let's go through that process quickly. If my equation is s squared plus 2s plus 2, then I know immediately that minus 1/2 of this is the real part of my root. So I'm going to go, this is going to be minus 1, right? And that's going to be minus 1 going from the origin of j omega out to my root location. Here is going to be minus 1 because minus 1/2 of the 2 is minus 1. And that's omega n squared, so omega n must equal the square root of 2, like so. So I immediately know where my roots are. I might have to solve for my omega d. My omega d is going to be 2 minus 1 square root. So what is that going to be? 1? It's going to be 1, isn't it? Yeah? Is it? Isn't this going to be 1? 1 squared plus 1 squared 2 is 2, the square root of 2. So I can immediately put my roots in there for the equation. From this, you should be able to write the impulse response by sight. Okay? So here's what you want to put in your pocket, write it down somewhere. The impulse response, y of t, from the impulse, is equal to twice the residue of that pole, P1, twice the residue of the pole, e to the minus, e to the sigma t, or minus zeta omega n, e to the sigma t times the cosine of omega d t minus the angle of the residue of that first pole. This formula always works. As I told you before, I am not going to derive this formula. I will not derive it. It is in your notes. I will begin to go over it with you and show you why it's true. But whenever I want the impulse response for any pole anywhere, I just apply this formula and the impulse response falls right out. All you have to do is remember what's that residue. How do I get the residue of this pole, which determines the magnitude of the cosine function and the phase angle? And I get the residue by drawing phasors from the zeros, putting them in the numerator, and drawing phasors from the poles and throwing them in the denominator. Right? So, like we did before, we've done it. Trust me, don't tell you haven't done it. We've done it. If you want to evaluate this function at P1, you draw phasors from the zeros. I got no phasors from the zeros, so what do I put if there's no phasors from the zero? I put, not 0, I put 1. Yeah? So the residue of the pole is equal to 1, and that's all the products of the residues from the zeros, because there aren't any. What's the residue from the pole? Okay? Now, if you say we haven't done this before, I'm going to turn into the Wicked Witch of the West, just fly up to the ceiling and explode. Okay? We draw a phasor from the other pole, like so. We call that LP1. That's the phasor from the other pole. And that goes in the denominator, right? So the denominator is going to be 1 over LP1. Yep. And that turns out to be 2 omega d times j. Yes? Now, if you don't know what I'm doing, you haven't looked at my complex number 4. I got 4 videos that show you why what I'm doing works. I don't care if you know why. I just care that you be able to do the answer. But if you want to know why this works, you got to go through the videos. I haven't got time to go through each of you individually over and over again. So, what's the angle for this? For J? What's the angle for J? The angle for J. The angle for J. 90 degrees. It's in the denominator, therefore it's minus 90, yeah? It's minus 90. So this turns out to be equal to, omega d is equal to 1, right? Omega d is equal to 1. So omega d equals 1. So this turns out to be 1/2 at an angle of minus 90 degrees. Now I went real slow again. I know I'm going to probably have to do it again. Right? You have to know, just put a thing down, you have to know. Go back in your notes and you'll see that the last time I did this, I said you have to know how to do this. So you have to be able to evaluate the residue at that pole to give me the impulse response. Right? I'll do it again next week. You'll say you didn't have it again. So we're going to do that. I'm just used to doing it again and again and again until finally you get it. Put this formula in your pocket and you got it. So, what do I have then? This is y of t equals twice the residue. Twice the residue is 1, yeah? So it's going to be 1. E to the sigma t, what's that? E to the sigma t. What is it? E to the, what's sigma? What's sigma? Come on, folks. Minus 1, yeah? E to the minus t. What's the time constant? Time constant is the envelope, right? So the time constant is 1 second. This envelope, the envelope this thing is going to oscillate in, the envelope is going to die down. So I can already draw the envelope. I can already draw the envelope. It's going to look like this. And at 1 second, this thing is going to be down. All right, it'll be at 63% or 37% of its final value. So from the time constant, which is 1 over zeta omega n, equals the time constant of the second order system, right? I can draw the envelope that this thing's going to oscillate in. And it's going to oscillate at the cosine of omega d. What's omega d? 1. So it's going to oscillate as cosine of t minus 90 degrees. Yeah? Cosine of t minus 90 degrees. And you're done. You know that the cosine of t minus 90 is the sine, so this is going to be equal to e to the minus t sine of t. You don't have to do that last step. But what it means is this thing's going to oscillate inside the envelope like this. It'll oscillate like so. And it has a time constant. Okay, I get it. So this will be the impulse response of that system as it dies down to 0. If I put an impulse energy, if I put a spike of energy in it, that's what I'm going to get. You have to know how to do this, otherwise you won't understand what the root locus plot's telling me. You won't understand it like you understand it now. But I mean, you really won't understand it. So you have to be able to look at the roots and see this function coming out. I'm going to let you go, but I want to show you the power of this method. What's the step response? How would I do the step response? So I'm not going to screw around with the motion. How would I do the step response? Step response would be 1 over s, right? So I could either integrate this to get the step response. If you know how to integrate the sine function, you could do that. Or you could put another pole in. Because that's going to be your step. Yes? Yes? So what's going to happen to the residue of this pole? I'll have another one in the denominator, won't I? You see that? And the residue, this in the denominator for the step response will be LP1, LP, I'm going to call it LP0. LP0 is going to be this guy. So now this is going to be 1 over 2 omega j. That's still the same. But this guy over here is going to be the square root of 2 times whatever angle of 135 degrees, yeah? An angle of 135 degrees. So you can see that the step response is going to decrease the residue of the time response and increase the phase, the negative phase. I'll also have a response from this pole. How will I get a response from that pole? Well, I'll draw phasors from this pole and from this pole. The angle will go to 0 because the angles add up to 0. So the response for this pole is going to be 1 over the square root of 2 squared, or 1/2. So my steady state value for my step response will be equal to 1/2 plus this formula applied to that phasor. And do you see it? I could do it for the ramp. For the ramp, I just have 2, right? And do it again. And do it again. So I can visualize in my head what's happening to the impulse response of this function as I move things in. I put a gyro on there. Or I put an actuator out here. I put an actuator. Well, now I'm going to have a phasor from that actuator drawn to those poles. right, of a phaser from that actuator, it's going to affect this response. Gyros, I put 2 gyro poles out here. How is the gyro pole going to affect the impulse response? Well, I have to go through that and visualize what happens to the, you'll see that if you put the poles farther out, nothing happens. We'll cover that later. But before I show you why nothing happens, I want you to see what's going on. Right? Otherwise it won't make any sense. Yeah, yeah?
How would the impulse response change like different poles? Because like just by looking at it, like RP over.
Wait. How would the impulse response change with different? There's only 2 poles.
Yeah, but aren't you like looking at the impulse response at a certain pole, or is it just?
Yeah, the impulse response. That's the only one I've got. That's the only pole I've got.
Hold on to 0, like the origin.
The sister pole.
That's for the whole system.
That's for the pole and the sister pole.
Okay.
This response at this pole is for the pole and the sister pole.
Okay.
Okay? All right. So, if I wanted to do it totally correctly, I'd have to do the partial fraction expansion. For this pole, draw the phasors.
Okay.
Then partial fraction expansion for this pole, draw the phasors.
Okay.
I'll see that the residues for each phasors are complex conjugates of each other.
Okay.
And when I'm done, I'll apply the Euler identity to turn it into a cosine function, and I'll get this.
Okay. So that's all.
That's what I'm skipping. I'm skipping a page of mathematics, right? I'm skipping a page of mathematics that converts the partial fraction expansion from this and this into this. Because for our purposes, we just want to be able to get this from looking at that. So what I want you to know, you can go back and look at it, but you obviously you can't derive this every time, right? You've got to just do it. So what I want you to see is that the sigma, the envelope decay comes from the real part of the pole. The oscillation frequency comes from the negative. The magnitude of the function and the phase come from the residue. And the residue comes from the phasors drawn from the zeros. That's why if I were to put a lead in here, if I were to put a lead like that, you see how the phasor is going to give me more lead than lag at that. So I will add lead into my cosine function over here. Those are the kind of insights that I want you to be able to get to eventually as we do this stuff right now. Okay? So again, if you're having trouble with this stuff tonight, anything I covered today, we should cover tonight. Go in some depth. But I'll show you in your notes or in my notes where I derive this. If you want to see it in depth, why it works. It's worth, actually, if you look at my videos handhold you through it once. And then I say, okay, we've done it once. Now just put that in your pocket. All right, everybody, thank you.